Good afternoon, everyone, and good morning to sir. So, we would like to introduce Professor Richard Waals, sir. So, he is a professor in Structure and Fire Engineering Department at Stellenbosh University. He is head of this research fire engineering research unit in this unit. He is basically a civil engineer with fire background. Usually for us, this is a area where we don't usually get experts in this area. Civil engineer with fire background, you usually get basic fire engineers. So his expertise will be basically focused on in the area of design of steel structures in fire, analysis of structures in fire, fire forensics, and all those things. So Stellenbosch, for everybody's information, is a place in South Africa. If you have not heard about, it is and Stellenbosch University is one of the oldest university of that state, and it has been started in 1918 with various fields like humanities, science, engineering, and just like other engineering courses, we have electrical, mechanical, mechatronics, industrial engineering, chemical engineering. They have all these courses, and this fire engineering is one of the part of the civil engineering department. And this year they have also started master's program. They also have PhD programs. So students who are having an interest to pursue outside India, you can give a thought to this university also. Later on, you can also connect to sir, because he is also working in specific areas of fire. So if you have an interest to do higher studies, so Stellenbosch is also one of the universities you can think about. So today we would like to give a small introductory talk on the fundamentals of structural fire engineering, because as you know, in fire there are different parts, and structural fire engineering is one of the important areas where most of the people give least importance, because you don't get experts on that area. So today we would like to introduce Professor Richard Waals, to give a talk on this specific topic and enlighten our students. Before starting the talk, I would just give two instructions to the students. One instruction is that I would like to ask everyone to keep your mic on mute so that you don't disturb the talk. Next is that in case of any question, you can put your question in the chat box. We will review it in the end so that the flow of the discussion is not disturbed, and we can take up the questions in the last. Okay. So let us start this expert section. We welcome Professor Richard Waals again for this talk.
Great. Good afternoon. Good to meet all of you this morning. So Richard here from Stellenbosch, and glad to be able to present to you this morning. So I'm just going to start sharing my screen. Just going to make sure you can see it. Great. Can you see my screen now? Oh, you're on mute. I just want to make sure you can see my screen. Yeah,
yes, it is.
Sorry,
yeah. Now it is. We are able to see.
Great. So so this is if you want to find out more about what I'm going to be discussing, well, in general, what we're up to, we've got a website, fire.sun.ac.za, and then we've got a master's in fire engineering, and then so that is got more information about what we're up to. There's also a PhD and all sorts of things. So I'm specifically presenting on structural fire engineering, fundamentals of structural fire engineering today. And if I understand correctly, at least most of you have been exposed to it. Just want to get that out the way so I can see chats coming through. Most of you had sort of a basic knowledge over this, hopefully. And if there are any problems as I'm presenting, just shout. I mean, hopefully we don't have any technical glitches. But yeah, so if you want to find out more, we also have a YouTube page, Fire Sun, Firesun. And so various videos are available. And that'll help cover various topics. Some of that I will be discussing today. And then, we've got MEng and PhD programs, masters and short courses, online distance learning. MEng we launched in 2024. We do research, consulting, expert witness, development work for industry. So we're involved in a whole variety of different topics. So I mean, this is work from a previous thesis. For instance, there was a PhD looking at the behavior of structural steel systems in fire. But we do a whole range of research in fire. Yesterday, we were in the laboratory doing testing on lithium-ion batteries. And so there's a lot of different work going on with our team. So where I'm going to start off with is the basics. Just a bit of a background before we get into structural fire engineering. I want to just discuss structural engineering first. How are loads applied? And so you understand load paths if you can answer the question. If a fly lands anywhere on the building or you blow on it, how do those loads reach the foundation? So this is a cross section through a building. If a fly lands right there, what is the increase in the foundation reactions when the fly lands? Or if there's one apple on the roof, one apple weighs about 1 Newton. And so if you do sum of forces, if you put one apple on the roof, then the reactions, the support of the foundations and the load of the foundation should increase by 1 apple. So there's your apple, and then you would have your reactions. You have 0.6 apples and 0.4 apples left and right. And so this is the very basics. And the same thing, if you've got a gust of wind on the left-hand side of your building, you'd have some of the gust ending up in the one foundation and some of the gust. And these are tiny little forces. So you have load paths. And as long as we can make sure that there is a path from where a load is applied to a foundation, then we have a safe building. And we need to make sure all the pieces between where the load is applied and where the reaction is are strong enough. So we need to make sure that this column here, all the loads that are coming through this column can be carried, and same thing that side. So that's where we need to ultimately end up. It's a lot easier in ambient conditions. So when the general loads of the building on a day-to-day basis are applied, it's easy. But when it comes to fire, it gets far more complicated, far faster. So I will go through different structural systems and how you design for those. And if you want to make a mistake that causes a building to fall over, get load paths wrong. So for instance, this would be a building. Let's say this is a very simple industrial structure. And when the wind blows on it, you may have some loads, which are those red arrows. So that's trying to push the structure sideways. Now, you could have load paths in buildings. You've got your columns carry your vertical loads. So all the loads downwards are carried by your columns. But firstly, let's say a person is standing there. It's carried on the red beam to the columns to the foundations. You've also got bracing shear wall systems carrying lateral loads. So just to think about it, if this is a plan view on a building, so there's your columns, there's some beams in black and some main girders in green. And then you've got a concrete floor. And let's say the concrete floor looks like this. It's just a deck. You've probably seen these in buildings. Since vertical load paths are much easier to understand, let's start with them. So the load path is your floor. So you would first design your floor and make sure when the floor is designed, it sits on these beams. Then I would need to make sure that the black beams in plan, these are strong enough to support my floor. So I would design a beam spanning a few of these. Then let's say I design that beam next. So now I've got a secondary beam. So that is then a beam. It is supported, and then it sits on the other beam. Then I've got my primary beam. So the hatched area, the colored area, is how much load it carries. So the floor carries this. It sits on this beam. That beam carries that. And ultimately, then I've got this main green beam. It's carrying all this load. So kind of half the load goes this way and half the load goes that way. And then that is all the load carried by this green beam. And then ultimately, then you've got a column here. So then this whole area is what's carried by this column. And then from the column, it would go all the way down to the foundation. And we would need to make sure it's strong enough. It can carry the loads, the imposed loads, the permanent loads, the people, the concrete, the steel, whatever type of building it is, the timber. It can all get to the foundation, and every piece of it is strong enough because it's like a chain. The chain will break based on its weakest link. So if one of the links is weak, it falls down. So let's say now I'm going to now do some calculations. So let's say now I was modeling this floor. So I looked at the floor. There were 2 meter spans. I would have a beam. I would then, for instance, have a 10 kPa, 10 kilonewtons per square meter, or 1 ton. Let's say this is a 1 ton load per square meter, and it spans 2 meters. So I would design this beam. Well, this is my concrete floor slab. I would design it, and then it would be supported. Those little triangles are a support. That's what holds this black thing up. So there we go. I'm designing that. And for instance, I would get a reaction, let's say, of 20 kilonewtons per meter. So there's 2 tons, 20 kilonewtons is 2 tons. So at each point, every 1 meter width of beam needs to support 2 tons. Great, 20 kilonewtons. And so now let's say I design this little section here. That would be now this main beam. So I've got a steel beam there. It's sitting on the green girders. I'm now designing that section. There we go. So I've got 20 kilonewtons per meter. That would be the purple load from here. It's now applied here. And I would now design this beam to span from this side to this side. There we go. So I can then now find what is the reactions. What do the main girders have to support? Each side I have to support 80 kilonewtons or 8 tons. So my load from my slabs span to my secondary beams, beams to my primary beams. Great. Now I design my primary beams. And there's now an 80 kilonewton point load, 8 tons at each point. Cool. Now I've got my primary, or my girder, and let's say now the black beams are the little ones, and I'm designing this whole area. And at each beam, I've got a beam from the left, beam from the right, so I now have 2 point loads, one from the left, one from, so it's 160 kilonewtons, 16 tons. And I would put 16 tons, I would design my beam to span from column to column, and ultimately I get a reaction of about 240, because it's 160, 160, 160, 480, 480 divided by 2 gives me 240. There we go. I have now the force on the column from each beam, and then from each column I have some more load, and ultimately I get to, for instance, 640. The exact numbers are not overly important. All I wanted to show you was you have a load transfer through a structure, whether it's in fire conditions, whether it's during an earthquake, whatever it is, the load passes piece by piece by piece and gets to your foundation. If any of those pieces break, it falls down. So ultimately, that is what your job is, to make sure it doesn't fall down. And it doesn't matter whether you're the fire engineer or the structural engineer, you get involved in this, because the fire engineers may specify the requirements for the structure. And so that's what I will now start covering, is how to get there. Once you you may even need to design the foundation. For instance, if you add up the loads of all the floors, you'll get now a force load at the foundation. And then maybe you even need to check the soils underneath and make sure that the soil is sufficient. And then make sure your stresses don't fail the soil. This is not of issue to a fire engineer. Fire doesn't affect foundations and soils typically, so that you won't often get involved with. But ultimately, you can apply this whether it's small or big. This is a big building I designed some years ago, and high loads, etc. So you can design this for various requirements and get it ultimately to work out. Now, when it comes to the design of structures, my assumption is the Indian Code of Practice is probably similar to the South African Code of Practice. Ours is based on the Eurocode. And if you go through, the requirements are probably not very different. I may be wrong. But for instance, if you look at our Code of Practice and you search for the word fire, it comes up 11 times. Now, if you go ask most structural engineers, do you need to design a building for fire, or is it your responsibility to design for fire? They probably say no. They say it's the fire engineer's job to design for fire. Okay. But you've got various design conditions in the structural design code, and it's useful if you understand these code guidelines, because it's probably the same there. And you have what's called accidental actions, which is something that you don't expect. You do expect wind, you do expect people, you do expect furniture and concrete and steel. Those are normal loads. But then you also get accidental actions. And you also have an accidental design situation. Design situation involving exceptional conditions of the structure or its exposure, including fire, explosion, impact, or local failure. So you actually need to consider that in your design. It's an accidental design situation. And if you have a look at requirements for structural integrity and robustness, a structure shall be designed. And whether it's a Eurocode, an American code, or an Indian code, I'm pretty sure all of yours will have the same sort of phrase. A structure shall be designed and executed in accordance with the limit states procedures of whatever code you're using for unidentified and identified accidental design situations. So, hey, in order to provide compliance with the basic requirements. Abnormal events involve exceptional conditions of the structure or its exposure to fire, explosions, earthquakes, etc., etc. So you need to design for fire. And then, for instance, this would be limit states, and they're different limit states. So if you're not familiar with the term, it's what sort of conditions do you need to satisfy? And the first one is make sure it's strong enough. The second one, make sure it doesn't fall over. The second one is make sure the foundation or the soil doesn't fail. This one is an accidental limit state involving accidental and seismic actions. Make sure even if something that's not expected occurs, like an earthquake or a fire, it is still strong enough. It's not going to fall down. Damage is accepted. You allow your building to get damaged, but you don't allow it to fall over. You also get fatigue failure of the structure, and then in the case of the fire, structural resistance shall be adequate for the required period of time. So you must check fire resistance. This is typically very badly done in practice. Often, everyone assumes everyone else is doing it. So the fire engineer assumes the fire engineer assumes the structural engineer assumes the architect will do it, the architect thinks the fire engineer, and no one does it. So often protection of the structural skeleton for fire is very poorly done, but that is just the nature of the beast. So what is failure? What are the failure scenarios that can occur? Well, imagine now if you designed this building. Imagine you were the engineer, you designed it, you signed it off, you said, here you go, you have a building. Now, this was the famous Cardington tests done in the UK. And what you will notice with this structure is they ran a large-scale fire test in it. Very, very extreme damage to the structure and major floor deformations. Now, imagine if you arrived at this building, would you think, hey, this is a success, or hey, this is a failure? Well, it depends. So if all you're looking for is structural resistance and you want to keep people safe, this is okay. You will have to demolish the building. You will need to rebuild sections. And that may be acceptable if the fire is so severe that it causes this level of damage. As long as no collapses occur, this might be sufficient. But for instance, if you have compartmentation, you may have failure. Because, for instance, as the floor drops, perhaps now the fire can jump over or underneath walls, and that could be a problem. So that you might need to look at and be careful regarding. But that gives you an overview of things you may need to think about. So what is failure? Well, our local codes, and this will be very similar in your code, American codes, etc., etc. You'll typically find that the ISO 834, the EN codes, the Euro codes, the ASTM codes, etc. They're all basically the same as this. If you have a floor, the requirements of a floor wall are stability, strength, or structural resistance. Is it strong enough? Load capacity and deflections. If it experiences a fire, will it fall down? Yes, no. Will integrity be maintained? So this passage of smoke and flame through the slab must be prevented. Or I, insulation. This limits the amount of heat that is allowed to pass through the slab or wall. The average temperature rise of the upper surface may not exceed 140 degrees Celsius, and the peak temperature must not exceed. So you have these requirements. And if you want a wall to pass a fire test, you need to satisfy all these criteria. Is it strong enough? Can smoke and flame pass through? Can it prevent heat from passing through as well? So if you had a really, really thin steel sheet, it heats up so fast that something on the unexposed side can ignite, boom, and so you'd need to check for this. So for instance, you would need to check structural adequacy, integrity, insulation. In some codes, you can actually have different. For instance, you may have 120-minute structural, 60 integrity, and 60 insulation. That may be sufficient depending on where you are. So this is just a description of what is failure. What is the sort of failure requirement that you are looking for? And this is important because if you understand this and you are designing fire safety systems, you can specify them more easily. You can sometimes look at something and go, that's not going to work. A thin steel sheet is never going to function as a firewall because even if it prevents smoke and flame from passing through, the insulation requirement will fail really quickly. It's too thin, too highly conductive. energy will pass through and it will fail. So this is where you need passive protection. You need systems to protect your structural elements, beams, columns, slabs, whatever it is. Passive protection is required to keep structures safe in the case of a fire. The way who determine it, who specifies it is. The architect and the structural engineer stare at each other, and the first person who blinks gets the job. That is the sad reality of passive protection. Normally, it's everyone's fault and no one's fault, and it's forgotten. So it's a big issue, but hey, it's probably the same in India as well. The fire engineer has already said it's not part of his or her scope, or hasn't been appointed yet, or has the notes on his or her drawing say it's the structural engineer's job. So, hey, so what are your steps to rational design? So you've got to develop fire scenarios, do heat transfer calculations, and then do structural design. So firstly, what is your fire? What is the scenario your structure has to satisfy? So you'll have that red fire, which we'll discuss soon. This is gas temperature versus time. So you would have your time temperature scenario. Once you know what scenario you have, how hot does your structural system is? For instance, this is a heat transfer analysis through a wall. There's let's say a gypsum board with a steel stud with another gypsum board. This is just a normal drywall. And the fire is exposed to, the fire is applied there. And then you look at the heat transfer and would the system be strong enough to carry the load after 30, 60, 90 minutes? Then you would do your structural design, calculate structural loads, calculate induced forces due to fire, design members at elevated temperature. So you make sure that your structural elements are now strong enough. So what's your fire? How hot do your elements get? Given that you know how hot the elements get, will they collapse? Will they be able to carry the load? So everyone happy? You got that so far? Everyone's very quiet. Everyone making sense? Thumbs up? Let's just check that my class is awake. You following me? Yep. Okay. At least one person is awake. Great. So this is based upon the standard fire. We have 3 general fire curves we use commonly. The primary one is the standard fire curve. It's this red line. And it's kind of based, well, very cynically based on how fast 3 guys could shovel coal into a furnace. It is a furnace curve. So it's how hot you could heat a certain furnace to. And you would then test structural elements in that furnace. So there you go. It would heat up, heat up, heat up. And you make your furnace follow this. And you have your beam, slab, column, passive protection system in this fire. You expose it and you see how hot does it get after this amount of time, and does it survive? So it's a standardized test. And there are equations to categorize it. So if you have a real fire, though, it's a bit different. This is what you do in a furnace. This is what happens in a real building. So in a real building, you have ignition. Then the fire slowly starts growing. You get to flashover, growth, fully developed, decay, etc. So you have a distinct ignition point, and this is then temperature on the y-axis. And as the time goes by, smoke is being emitted, people are evacuating, the fire is growing, the couch catches fire, then the ceiling catches fire, etc. And then you get to flashover, which is a transition from a localized fire to a full room involvement fire. So it's a rapid transition. Sometimes flashover is seen as not a phase, but a line. That's fine. Then you have your fully developed fire. Then you have your decay period. So fully developed, it burns as fast as oxygen can come in. So it's ventilation controlled. And then once the fuel starts burning out, then you go into the decay phase. So let's now think about how tests may influence that. So for instance, if you have, apologies, some of the text didn't pop up. So you first have what you will do, it's called reaction to fire. So the first thing you want to do is test for reaction to fire. Will something ignite? And if it ignites, how fast does the fire spread over the surface? So let's say you've got timber cladding or insulation materials. If they ignite, how fast do they allow fire spread? Okay, now that we have ignition, you may need to test your detectors, your smoke extraction, or even your sprinklers. So then you have other systems you will test. Then, given that the fire is now growing, it's getting to the fully developed stage, then we need to make sure our structure satisfies fire resistance. That is, fire resistance is captured by that standard time temperature curve. So here you have a purple curve, the standard fire curve. So that now tries to kind of mimic this fully developed phase from ignition through growth, etc. And then ultimately you do not have a decay phase. So with a standard fire, you kind of just capture it. But one thing though, the standard fire tells you absolutely nothing about this early phase. So for instance, most people would die here. There's a fire, there's ignition, smoke is spreading, and the smoke kills people. So normally what you would have in the room is you would have ignition, smoke spread, so you'd have death here. If it's in adjacent rooms, then fair enough. You may get flashover in room 1, smoke spreading to room 2, 3, 4, 5, and then those would be in kind of this phase. But normally people die before the fire resistance curve becomes relevant. If your structure is being affected, people are dead in that room, and you'll see why I say that soon. But so that's what we're trying to capture with the fire resistance, and this is what we capture with reaction to fire. And people get confused by this topic quite a bit, because for instance, a timber wall can have a fire resistance of 2 hours, but it ignites and it burns. So it's got maybe a poor reaction to fire because it does ignite, it does burn, but because it is a thick timber wall, it satisfies fire resistance requirements. It takes a long time to char, it slowly burns through, and so you can get your integrity, insulation, and structural resistance. So this would be a reaction to fire test. A material is there, it's been exposed to high intensity radiation from a cone calorimeter, it heats, it produces pyrolysis gases, and eventually bang, you have ignition. And now you would measure the heat release rate coming off the material, and ultimately this would tell you a lot about the reaction to fire properties of this material. So that is a reaction to fire test. Then you do also, though, have different ways of capturing your, just as an alternative, just to go back. So we have our standard fire curve. You don't always use this in every situation. So what you can do, though, is design for something a little bit more realistic, but it's very difficult to generate this real-time temperature curve. So for instance, what we can do is have a parametric curve. It's kind of a halfway between your real fire and a standard fire. So you have some equations that are not difficult to do. You can put it in a spreadsheet, and you can generate a curve that has a heating phase and a cooling phase, and then it dies out. This is a burnout fire. So for instance, the room you're sitting in at home or in the university may require a 1-hour fire rating. So that's in the code. It says you will have a 1-hour fire. But let's say now you wanted to design it more efficiently. So then you have a look, okay, in the room I am in, what's the fuel load? What's the ventilation? And then from that, you can generate a time temperature curve, which describes the fuel and the ventilation in the room. And then ultimately, if you design for that curve, you have a burnout fire, so that it burns, 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 burns out. And if your structure is strong enough after this fire, then you're happy. Because even in a worst case scenario where all the fuel is consumed in the room you are, it still doesn't basically burn up, you're good. You now have a case where you are likely to, you've got a case where even the most severe fire will be sufficient, but the result will be different. So this is a sort of a realistic-ish fire. It has a heating phase and a cooling phase, and it's fuel controlled and then ventilation controlled. So initially it's how fast it can burn, and then, well, hey, you have ventilation controlling it, and then it dies down. So you can also have other curves that you generate. For instance, zonal models, CFast, ozone, etc. CFast, great piece of software, very easy to use, probably a bit too easy. You can generate real garbage if you don't know what you're doing, but it's a nice piece of software. Hot layer at the top, cold layer, and then it also transitions from hot layer to global single zone. So you have zonal models that can estimate the temperature of the hot layer and the cold layer. So that software you can get and play with. If it gets really complicated, you can also use computational fluid dynamics. So this video you will watch is actually from a forensic investigation we did. This was a very, very expensive fire, caused large-scale damage to some key infrastructure. And we went there, did investigation, and from eyewitness accounts, it appeared that the fire started there next to a certain room. It ignited, and then the fire spread through the room. And what you will see is that the combustion is occurring right along the edge there. So there's ignition, and then there's lots of fuel stacked around, ignite, and then it spread, etc. So this was then a fire that spread through, and you see it ran out of oxygen in the middle. So you see the fire moving towards where it can find oxygen. It ends up only burning at the openings, fierce burning at the long window on the side, and it burned for many hours. This was a 20-hour fire, very severe. The fire department really struggled to put it out. It was a bit of a disaster, and ultimately led to structural collapse. So there's the sort of temperatures you get. You'll see in the flame zone, you've got more than 1,000. But on the inside, because of this ventilation starvation, so oxygen starvation, way too little ventilation for the size of the room. Once the fire grows, so there's the temperatures, spreads out, and then, oh dear, it actually gets a lot cooler. And so you can use this to also then predict what the temperatures would be in a real occupancy. You can also have localized fires. So for instance, if you have a transformer or something. So a transformer fire, a pool fire, a petrochemical fire, a tank fire. You can have a localized fire where it's got a distinct diameter, a heat release rate that you can calculate, 500 kilowatts a square meter or 1,000 kilowatts a square meter, depending on your fuel. And then the hot gases rise and then disperse, and you may get sealing jets. And this you can also use to predict the behavior and temperature that you would use, and then you can design your structural system, your walls, your slabs, whatever it is for this. You also get traveling fires, worked by Clifton. So for instance, you have your near field, as your far field, as the fire moves through the building. It's a lot more complicated to apply these. That's why people normally use the standard fire rather than a parametric or CFD. But there you go, it gives you some guidance. So as I said, this is now to go back to enclosure fires: ignition, growth, flashover, fully developed decay. And this is your time to escape from a compartment. This is your standard fire resistance. So just to emphasize that differentiation. Now, how do you test? Because I've been talking about testing now, and this is what a furnace test would look like. So this is a big box, insulated, burners on the side. This is some diesel burners pumping in hot gases. And then if the gases on the inside, the hot gases, they adjust the burners to hit the standard fire curve. And this is a door. This is a door fire test. And you can see now, hey, the door starts failing, fire starts, well, smoke comes out. So that's an integrity failure. There's your integrity failure again, fire coming through. Uh-oh, that's not good. And ultimately, then you have a failure of the door. And so this would then be measured. So for instance, 10 minutes or 30 minutes or 90 minutes. And so, as I said, the box, the big burners, everything inside the gas temperature follows the temperature curve, standard time temperature curve, and you see how long does your element withstand this. If failure occurs, then you end up with something that looks like this. When you have fire spread over multiple floors, this is a colossal failure. This building, I'm pretty sure, was ultimately demolished. And you had a compartmentation loss. So fire spread from floor to floor to floor to floor to floor. And yeah, that thing is toast. So it will need to probably be demolished. I'm not sure what the final decision was. So let's start having a look at different structural systems. Let's have a look at how you design steelwork, concrete, timber, and composite for fire resistance. So in terms of steelwork, steel's possibly on the simpler side. You can rationally design it. You can save a lot of money. What you need for steel is passive protection. So you coat the steelwork with a apologies, with a board or a paint or something else, and you make sure that the steelwork holds out. Then you have concrete, and what you do with concrete is you make sure that there's concrete cover, that there's a sacrificial layer of concrete on the outside to protect your reinforcing steel, your rebar in the middle. Your timber, you have sacrificial cover, so you let the outer part burn and the inner part hold on. And then you've got composite, where you have passive protection and good rational design. So you can also design composites, so steel beams, concrete floors. These can actually be designed to be very efficient. Now, steelwork and fire, it is possible to have unprotected steelwork. Only critical members need to be protected in certain types of structures, such as composite floors. Protection is done using boards, intumescent paint, spray-on products, concrete casement, etc. Connections can be very important. Is it often connection failure triggers? So, for instance, here's different beams, and then you would want to look at what's your exposed perimeter divided by your cross-sectional area. Because, for instance, this beam here, this beam or column here has a lot of perimeter where fire can affect it and heat it up. So this will heat up very quickly. But for instance, if you had a concrete slab and a box, the perimeter is much lower. So even though the beam is the same and the fire is the same, this will heat up faster than this one. So you can optimize your design, and there's a lot of money in these passive protection systems. So you can optimize the passive protection design to bring the cost down by going from A to B. Okay, so these are some products. For instance, this is an intumescent paint, and you can see how they swell. So it provides a low conductivity material, and ultimately, provided that doesn't fall off, it gives you a good insulation to make sure that nothing happens to the product. So that is how the different products behave. But there are a whole variety of these boards, slabs. The board systems don't activate, but these the intumescents do. The biggest problem with an intumescent is often they get too heavy and then they just fall down and then they're useless. So you've got to make sure in a test that they don't delaminate, that you don't have fall-off behavior, because it can very easily occur. Now, why would you want to rationalize the design? So this is in South African rands. The main picture is these are 3 different column sizes or steel sizes. This one's 23 kilograms a meter, this is 46 kilograms a meter, and this is 137. So it's small column, medium column, large column steelwork. That's the mass. This is the section factor, your heated perimeter over area or heated area over volume, same thing. And as this value goes up, it heats up faster. This is the cost of the steel in rands per meter. This is the cost of the paint. So you can see with a skinny member, the paint can cost more than the steel work itself. So on a big project, this can lead to a lot of money. So with good rational design, you can bring down the cost, make your client very happy, and then get to efficient solution. But also, as you see, as it gets thicker and heavier, the cost of the paint and the total cost of the paint relative to the steel comes down and down. So that's a good thing. You want to be able to do that. If, for instance, you want to go from 60 minutes to 120 minutes, you actually see the cost going up further and further. And so what you also may see is the cost of the paint doesn't double to go from 60 to 120. It may be 4 times or 6 times. Yeah, 4 times here. So the coating cost can be very expensive. So just be aware, and this is kind of old figures. This is 2015 numbers I have. I should update these at some stage. But yeah, it's good rational design can bring the cost down. So let's start thinking about steel and how steel is affected in fire. So this is the strength with temperature, the red line. So as it heats up to about 400 degrees Celsius, the strength doesn't drop, more or less. And then at 400, it quickly plummets, all the way to 1200. By 1200 degrees Celsius, your steel has lost its strength. But normally at around 550 degrees Celsius, 550 to 600, you've lost about 50% of your strength. So somewhere around there, 550, 600. So that's why you sometimes see these critical temperatures, a critical temperature, 500, 550, 600. And it's kind of roughly based on the load, the strength that you need is about half. So if you've lost half the strength, you're probably still fine. So here is then your steel stiffness. So what you find is deflections occur. So the stiffness drops first, but then your strength drops afterwards. So it deflects more, but then it also starts getting weaker. So that's your Young's modulus and your yield strength used to measure those. And as I was saying, your section factor, this heats up faster, this heats up slower. So you can also do different layouts to get to different solutions. And this passive protection will be cheaper than that there. Firstly, this is a longer perimeter, and it'll need to be thicker than this one here. The only thing is boards, you have to do a lot more effort, and this can look nice if done properly, but there are pros and cons of all the different systems. In terms of concreting fire, concrete typically does well. For most concrete structures, the most important thing is to ensure that there is sufficient cover to rebar. Concrete structures generally behave well in fire, although care must be taken with certain details. So here you have a structure. This was in a project I was involved with, very, very severe fire. All the concrete popped off, rebar was exposed, severe damage. This had to be demolished. You can actually see this column here is starting to buckle, that it's actually popping out on the side. So this is pretty complex. This is a lot, very, very little strength left. This is a problem. You don't want to put big machines in there to demolish it. You've got to be careful. So this is when the fire's been very severe for a very long time. So this fire lasted many hours. That was the problem. It was beyond what the building was designed for. One of the useful things with fire design is, especially with our local codes, and you'll probably find it similar with your codes, is often structural engineers focus on what's called cover. So cover is the distance between the outside of the concrete and the first piece of steel. And what you normally do, the cover is 25 or 30 mils, but the cover is actually of secondary importance to what's called your axis distance, because the fire is applied on the outside, the heat penetrates through the concrete, and more or less where it gets to the middle of this reinforcing steel, this rebar, that's what you're worried about. So if you use the axis distance rather than the cover, you can sometimes develop more efficient systems. So in the Eurocode, it has axis distance. So for instance, this is a table, and if you need a 30-minute, 60-minute, 90-minute, 120-minute structural resistance for different utilization factors, and the utilization factor is how heavily loaded is the column or beam in fire relative to normal. So normally your fire loads are roughly 50% of your ultimate loads. Not going to go into detail on how you calculate that, but often we're around there. Sometimes there are differences. So for instance, let's say you want a 60-minute structural resistance on a column. You need a 36 mil axis distance and a 200 mil wide column. So this base here would need to be 200 mils, and then you need 36 mil. So if you have a 25 mil cover plus a 10 mil bar, that's already 35. Oh, okay, it's easily satisfied. So you can use these, and this is pretty quick and easy. You can get to quite easy fire resistance ratings, just pulling numbers off tables, and then you can specify cover and this and that must be, and you go, great, I'm happy. So now this is what a concrete structure though looks like when it's been severely fire affected. I actually need to go back to the structure next week. Very large scale damage. This was the CFD model I showed you earlier. And the fire spread, you've got very severe structural damage, large scale cracking, spalling. This is turned pinkish. Pinkish tells you it's around 600 degrees Celsius in that vicinities. Buff color, so there's this fire spread affected this, permanent deformations. Chances are much of this would have to be demolished. What even happened in the structure, there's major structural collapse, there's spalling. This is a column. Now, this is a big column. This is a 600 mil by 600 mil column. This is a big chunky thing supporting, I think it was about 500 tons, if I stand to be corrected, or maybe it was even 1,000 tons, can't remember offhand. And it's very heavily reinforced. But what happened is that the beam actually caused this entire thing to fail, and it cut it in half, and about a meter of column is missing. On a perimeter column, the beams actually pushed it out and caused major, major structural cracking through the elements. So collapse of a concrete column. So for instance, here's your fire affecting the slab, and we're going to look at that column here. And this is from then a structural analysis following the other analyses. What happened was the fire here heated up the beam, and it was a very long, slow fire. So it gradually heated up, heated up, heated up. And ultimately what happened is this big beam here got hotter and hotter and hotter. As something gets hotter, it gets bigger. And when we arrived on site, we were actually asked, hey, could it have been an explosion or something else that caused damage? But I said, no, have a look. This is a diagonal cut through this column. And a diagonal cut is a shear failure. It's a horizontal force. And people, why? Hold on. There was a vertical load coming down there. How come there was a horizontal force that caused failure of this column? Well, what happened was this beam there expanded. Thermal expansion, push, 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 push. And it was an edge column here that failed because there was a retaining wall and there was nothing holding it back. So if it had been fixed to retaining wall, the retaining wall to hold it wouldn't have come down. Push, 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 push. And to the point it actually failed this column because this was about a 400-ton lateral force. So it's the weight of about 400 vehicles sideways. So you can imagine a cable hanging 400 utility vehicles, small trucks, and that would be the sideways force this beam exerted and failed this. So there you go. So you now have sagging. If you want to design something, so you can design beams and slabs and columns, so you can follow different calculation procedures. So for instance, if you wanted to design a beam, what you do is, there's your original beam size. You work out the heat or the temperature through it at different times. And for instance, you find your 500 degrees Celsius isotherm. And it's a bit of a rough and ready assumption, but what you say is everything hotter than 500 degrees, ignore. Everything here, everything here, everything in the, pretend it doesn't exist, and just now design a smaller beam. Structural engineers are actually quite good at that. So you just design a beam as if it's smaller, and then your steel here, you just design it at the temperature. So let's say it's at 600 degrees Celsius. You can now check the capacity with rebar, let's say that now has 47% the strength, and then a smaller beam, and then you follow the same design calculations. That's if it's sagging, so that's if the bottom's in tension. If the top is in tension, what we call hogging, you design the rebar within also a reduced cross-section, and then just your effective depth changes. Well, we're not going to go into that, but that gives you a kind of an overview of how you design a concrete element for a standard fire resistance. And this would be, let's say, 20 moles or 30 millimeters of concrete loss. But let's say now for a 2-hour fire, maybe you'd lose more. So there are standardized numbers that you can use to then specify the resistance you need. But one of the things is that people assume concrete is always safe, but not necessarily. What you find here is explosive spalling. So this was a test done at the University of Notre Dame. And here, the concrete was a high strength concrete, let's say 100 MPa or 150 MPa. And your dense concretes hold the moisture in because it can't escape. So when it heats up, your water converts into steam. Steam is much bigger than water, so it creates a pressure. Now it's pushing. And so it creates a pressure in the structural element until it blows. It actually bursts, and you'll have explosive spalling of your structural element due to the pressure buildup. And now, so that is now starting to require different test methodologies, especially in your high-performance concrete. So for instance, for tunnels, now for tunnel design, what they actually have is a little mobile furnace that you move it in, you put it on the side, and then you run a fire test and you see, would my concrete lining spall? Because you can't use this method if you have spalling, because this method assumes the concrete stays in place. But if you have explosive spalling, it's a big problem. So there you go. Just show you once again. Bang. Heat it up until the point where it actually blew. Quite scary failure. Very, very problematic. That would cause a lot of damage to areas around. You can also design composite decks. For instance, as I said, so composite deck is steel columns, steel beams, concrete floor on top. The BRE Cardington full-scale tests, amongst others, showed that composite slabs behave very well in fire, even when steelwork is not protected. And what you do to design these systems is that, for instance, this is a plan view of a building. You protect your perimeter beams, and then you just allow the beams between to fail. If they fail, so what? Because they hang. That picture I showed earlier where the floor hangs, it just hangs, and you allow for protection around the edge. And as long as those beams are protected, then you're fine, because this hangs from them, carries the load. You design your beams for the full load, you design your columns, and you're happy. So you can save quite a lot of money. So for instance, in this structure here, column beam, this shows you where the secondary beams are not protected. And so this would lead to quite a significant savings, because maybe you have 50% of beams, and the cost of this passive protection is high. So your client's going to love you if you can knock half the cost of the passive protection on your beams. And so that all goes through, but you would need to make sure your beams, slabs, columns, the white ones here are strong enough. So you design those and leave everything between. So this requires rational design. So you need to be quite careful with doing it, but it can be done to develop rational fire designs for composite systems. Timber, you also can get timber and fire. Timber structures with heavy members can survive severe fires. Outer char layers protect the inner layers of the structure. Timber fire design is done assuming that a certain amount of material is lost during the fire. So this would be the basis. So there is your original beam, the dotted black line, and the fire now occurs. And the material here gradually chars. Slowly eats away. And this will depend on the type of timber, but it may be between 0.6 mil and about 1 millimeters per minute. So let's say after 40 minutes, let's say you have 30 millimeters of char that has been eaten away. Then you also have a zero strength layer. So it hasn't been charred, but it has been heated. And especially if it gets above 100 degrees Celsius, wood has moisture in it, and the moisture will be affected and the strength will drop. So you have a char layer, a zero strength layer, and then you have a residual capacity. So basically your dotted line is the residual cross section. You use your residual cross section, and as long as the residual cross section is fine, then you can design for it. So what you want to make sure is that the beam is big enough, even after a 1 hour or 2 hour fire, it's still sufficient. And you can put products on. So let's say the timber is too expensive, you can clad it. You can put an intumescent coating on it. There are various things that you can do to try protect the timber and get to a result. So for instance, here is some connections that we tested in fire. And you can see there very clearly the char versus the non-char. Different connections are protected in different ways. So these ones here, these ones on the top had passive protection in the joint because there was a beam and a column, and where they tied together, we sealed the joint. So you can see where the joint was sealed, it performed well. These ones had no sealing, but that was a very tight joint, so the fire couldn't penetrate. That had about a 3 mil gap, 6 mil gap, 10 mil gap. So as the gap between the beam and the column got bigger, the fire penetrated further and further until that is a failure. That would have caused main structural collapse. That not necessarily. So you've got to be very careful with your design to make sure this is sufficient. So that kind of gives an overview of your main structural system. So we've had a look at, firstly, what were your design fires, whether it was a standard fire, a parametric fire, a real fire, which can be developed using computational fluid dynamics or others. And then we had a look at heat transfer. Then we had a look at steel, concrete, timber, and composite. And different structures come with different risks. So you just have to be careful now. Sorry, one thing I didn't mention is that earlier we discussed reaction to fire tests. So remember, reaction to fire is, can it burn? How does the fire spread? So a timber beam can have a good fire resistance, but a poorer reaction to fire. So when a timber structure burns, it's going to release a lot of heat. So you will need to use a more severe design fire. So let's say you used to need 30 minutes fire rating, you may now need 60 minutes. Because now your skeleton of your structure, your beams and slabs and floors contribute to the fuel, so they will burn more intensely. There you go. So now different structures come with different risks. Buildings can be designed to withstand fire. Fire scenarios should match the risk. So also, the standard fire scenarios are useful, but they are standardized. If you have a high-risk facilities, you should use a different design fire, not necessarily a 30 or 60-minute fire. You may need to use a more complex fire scenario. Standard fires are different to real fires, so I hope I pointed that out. And the early phase is where you have ignition, smoke spread, that's where people die, and then you have your post flashover where you have your general structural fire resistance. Restrained thermal expansion is the primary reason for damage to buildings. The building breaks itself up as it heats up. So in a real building, as I showed you with that concrete member, as it heats up, it exerts very high lateral forces, and it's those lateral forces where structural collapse normally occurs. It's very difficult to predict, but that is a major problem in real buildings, that expansion. And especially where it's got nowhere to go. It pushes, and it can cause shearing and failure of structural members. So you want to avoid against that. Good rational design can provide much safer structures. So what you can do with a high risk or expensive or fancy structure, you actually rationalize it. You go, what's my fire? What's my heat transfer? What are my load scenarios? And then you develop a rational design situation to develop an entire structural system. Your entire structural system would need to accommodate all these requirements to make sure it's strong enough, the smoke and fire does not spread, and then also it has sufficient insulation resistance. The heat transfer doesn't occur through it too fast. And so one or two final things, just for the hell of it, let's smoke some hemp. You have weird and wonderful emerging products. And sometimes you would need to then evaluate them. Now, what do you do, for instance, with hempcrete? This is a PhD thesis that's just been finished. It's actually out for examination at the moment. And so our student did testing. And so here is some hemp. And this was assessed under different fire ratings. So what you would find, for instance, this material, the outer layer, which had heavy fire exposure, was white, total char. Then you had kind of a gray black, a brown, and then unaffected. So this would be your residual cross section. So here is basically unaffected. And this would still be able to carry load. So if you needed the bricks to be load bearing, that would be all that's left. But it had a very low heat release rate, very little flaming. This picture is not from this test. This is pure hemp. So if you burn pure hemp, it burns quickly. Hemp is just a weed. This is the non-narcotic version we are talking about here. So it's just a plant, and then you can mix it up and you can make products out. You can make rope from it. You find hemp rope. If you burn pure hemp, that's what you get. If you mix it with a stabilizer, cementitious product, you can build blocks. And here you go. This is unaffected. And you can then do a rational design based upon this. And so you would test it and then even check what is the residual structural capacity. And so this part would fail, but hey, this part can still carry load. And then that would be in the furnace. So furnace tests were done to evaluate it. So you can do cone calorimeter for reaction to fire, fire resistance test to check charring and behavior. And then that would be a way to assess these sorts of products. So that would be as if you have a novel, unusual, non-codified product, how you would start assessing it. And there's a lot of these sustainable products coming onto the market with no fire design guidelines. So this is then we would put it through its paces, assess it in various ways, and then find out what was its fire rating, what was its reaction to fire, etc. And then you can evaluate it, whether it was safe or not. So yeah, so that's an overview of structural fire. Hopefully it has been useful. Still got a bit of time, so we've got probably about 20 minutes for questions now, which is great. So we can now start discussing through the aspect. But one more time, just to emphasize it, because I've got a few minutes here. The main thing I was just trying to explain were the steps here. What was your fire? What's your heat transfer? What's your structural design? And there are ways to design steel, concrete, timber, composite, etc. in fire that you can come up with safe solutions for a different system. So yeah, so that's that. I'm going to now swap across to some questions and then see. So you're welcome to post questions, and then I will possibly pop up and down in the presentation to find what's useful. So is IS 3809-1892 fire resistance test? Oh, is test of structures. Thank you. So I take that is a statement. So that is the local Indian code for fire resistance. My assumption is it's based on the ISO 834, the standard fire test as well. So what I showed you today, I'm pretty sure is the same requirement as in India. So that's good. Yeah, applicable for India. Great. How are cases varying where the heat release rate is limited but temperatures are high versus the other way around? So this comes back to the standard fire versus non-standard fire again. If you have a standard fire, the code says you shall have an hour fire rating. The code makes no allowance for heat release rates, etc. You just follow that curve and you stick to it. If, however, for instance, you have a more realistic fire scenario, you may use a Eurocode parametric code, and you can check for your development. So if you have very little ventilation, that would be this case, this dark blue line. What happens is it heats slowly because the ventilation limits it, but then it burns for longer. So what you see is the fire will last longer. So for instance, for steel work, this will be a less severe fire because steel work, the maximum temperature is important. So for steel work, high ventilation will give you a worse case. But for concrete, this may be worse. A long, slow fire is more dangerous to concrete. A short, hot fire is more dangerous to steel. So basically what happens is when you limit your ventilation, you limit your heat release rate, and so your fire will burn longer. And so it's a balance between your total fuel, your ventilation, and also the type of material, your room geometry. That will affect your length of fire, and then your total fire severity, and then the damage to the structure. It's very difficult to predict it accurately. So as I said, I mean, when you want to do a real fire, you end up with quite complex models like this that you need to run. That becomes quite difficult. So how are cases, yeah, so that I've dealt with. Can concrete blocks from bagasse good? Typically, concrete systems perform well, and with the addition of extenders, bagasse ash, fly ash, ground granulated blast furnace slag, etc., typically it has very little impact on the concrete resistance. So normally, I haven't checked the most recent research in bagasse ash if it makes any difference. I don't think so. I wouldn't expect it to have a significant influence on your results. Chances are the concrete would be give or take the same. Where it does become problematic is where you have high density concretes, well, very dense matrices, because then the steam can't escape. There are ways if you have higher risk concrete. For instance, you put polypropylene fibers in, little plastic, tiny little fibers in the concrete, and then when the fire occurs, they melt and allows the steam to escape. So it's actually one way of improving your fire resistance of your concrete without doing too much. So that's a quick thing. Why not bagasse instead of timber? Well, it depends on cost. So I think in somewhere like India, you have very little timber industry for mass timber. So yes, it wouldn't make sense to use mass timber. It'll be too expensive. In Canada, the USA, Scandinavia, the timber market is massive. They have huge forests, a lot of design happening, a lot of R&D work. So then for them, timber makes a lot more sense. Whereas I understand locally that's not commonly used, so it's less of a problem to you. So blocks and other materials will be more useful. Great, I think that is all the questions posted. I don't know if there's anything else that anyone wants to ask at this stage. What should be the ratio of fibers and concrete? I can't remember. If you have a look in a textbook, Buchanan and Abu, it's a great book. It's got a structural design for fire safety. Let me put that. Structural design for fire safety, Buchanan and Abu, and it has the details, and so that will help. Yeah, it's not high dosages. It's a couple of kilos per cubic meter type of thing. Factors affecting thermal conductivity of wood. So firstly, the different species of timber have different conductivities. So different densities also influence, because that influences your specific heat. So those have an impact. Additives, you can put additives on. You can put materials to reduce the ignitability. I'm a bit skeptical on most of these products. You get boron impregnated materials and fire retardants and calcium carbonate based materials that you can impregnate with. They haven't been brilliant at stopping fires. They may delay the time to ignition, but they don't make wood non-combustible. I'm yet to see a non-combustible wood. wood still burns. You just need enough heat. So it may delay the fire, but it's still going to burn away. So, hey. So yeah, you do get additives. They do help, but hey. Any other questions? I'm just checking the questions at the side. Any other queries or comments that you might have? Nope.
So do you have any other questions?
I'm here. I'm free.
Yeah.
Otherwise,
I think even one of our visiting faculty, Ms. Priyanka, has joined. She is also working in a fire industry. So she is a civil engineer, basically.
Oh, cool.
So,
great. Welcome.
Hey, it was a very fruitful lecture, I would say, especially for the students and fire engineering, because they are not knowing much about this structure. So I feel that it was very useful for them. I would like to ask one question, that how does the integration of the passive fire protection systems that will impact the life cycle cost of a building? Because I think probably it will help them to understand in a better way as a fire engineer. Yeah.
Very, very good question with not an easy answer. So the question was, how does it impact the life cycle? So obviously it's going to add on cost firstly, depending on. Sometimes like concrete may not add much cost because changing the cover may not necessarily change much. If you've got a steel structure, it's going to add on a lot of cost to the passive protection. If you design it well, the cost can come down. Often you'll need maintenance of these systems. So your passive protection, you may need to check. It hasn't been affected over the years, so that can be a problem. If it's a boarding system, so calcium silicates, gypsum, magnesium oxide, obviously now those may need to be replaced after 10, 20, 30 years, and then you've got to go back and replace them. All of them will add to the carbon contribution. Normally they're negative. Normally it's not a positive contribution to environmental friendliness. Adds to cost. So it's an expense and it is a maintenance cost. So it's not it's something that adds to the building. It's compulsory though, and I think I'm pretty sure in India legislatively you're probably the same as us. In our act and our constitution, it says you will provide a safe building. It doesn't matter how, as long as you must do it. And so if you don't provide a fire safe building and you sign it off, you can go to jail. If it falls down, collapses and kills people, they can, the lawyers are going to nail you. So that's where it does come in. It's actually a compulsory requirement to provide people constitutionally a fire safe environment. As I'm not familiar with the local Indian legislative environment, but South Africa, UK, America, Australia, most countries around the world, it's compulsory requirement. Okay, answer your question.
Yes, definitely. Thank you.
Pleasure. Great.
Yeah.
I see there is a question, strength loss graphs of wood versus concrete. Now, concrete, it a couple of 100 degrees Celsius and then it drops off faster. So I should have added some slides. I just got a really long presentation. Those are easy to find. The Eurocode has some good guidance. The big thing with concrete is not necessarily the loss of strength. It's a low conductivity material. So you actually don't care if you lose your outer 5 or 10 mils because it's a big bulky element. But you can look that up at about 500-600 degrees Celsius. I don't remember what the strength loss was, but first 2, 3, depending on your code, 2, 3, 400 degrees Celsius limited loss, and then it drops very quickly the strength of the concrete. Timber, much faster. At 100, you're already starting to lose strength. So timber loses it by 300 degrees Celsius. There's no timber left. It's charred. It's gone. So timber drops strength far faster. Great. Anything else? Any other questions people would like to ask?
Any other questions? I think they must be hungry. Yeah. So it was a very wonderful, enlightening talk for us. Maybe we can have later talks. Once we sign MOU, we can have talks on both sides, a series of talks which can help both the universities. I have also told them you can even ask questions about how to study, what areas, what are the scope, what are the opportunities, because there are many areas people don't know the fire, especially structural fire. You have EVs and all those things. So a session on that will be helping them understand in different countries what are the requirements. Many people don't know those requirements. So maybe we can have those sessions later.
Great.
I think you must be having a lecture today, maybe later.